What's up, guys? Welcome back to Vanover Machine and Repair. In today's video, we're continuing on with the theme of broken machines. So behind me is a machine that you have yet to see, and that is the Fryer MB16 milling machine. And up until this point, it has been running more or less, and it's broken. So I thought I'd bring you guys along for the ride. Steph knows with me. He's gonna give you some backstory on the machine, and then we'll jump right into the repairs.
Yeah, hey guys. Like Kyle said, this is one of our last purchases. It's a CNC machine, recent machine. It's a 2012 vintage, and it's very well equipped. Electronically, it has Siemens controls, and it's also a very robust and rigid machine with a lot of travel. So we were really hoping to use this machine for a lot of larger jobs. And it's been serving us very well, but recently we started having issues with the main spindle motor, which is just a normal asynchronous motor. But the quality is questionable, so isolation gave up. We started having shorts between the coils and ground that led to a failure on the drive. So we pulled down the motor already, we checked the bearings, we checked the isolation, we cleaned up the motor, which was very dirty. It didn't help, so now you see what's going to happen.
All right, guys, I want to bring you up to speed on the repair path that we've taken on this machine because it's been a little bit unlinear. So initially we had an error with the motor, and we thought that the motor was bad. So the motor on this machine is just a basic AC motor. We started by taking that motor down, and we did a meager test on the motor, and it failed. But the bearings were shot, and we wanted to start simple. So we start by taking the motor apart. We replaced the bearings because they were cheap and easy, and we cleaned the motor because there were a lot of chips and debris. We reinstalled the motor, and we were still getting an error. So at that point, we were convinced that the drive was faulty. So we ordered a drive, and the reason we thought the drive was faulty is after we reconditioned the motor, we bench tested it, and it seemed to run fine. So once we got the new drive, installed, and we still got an error. So from that point, we realized that maybe it wasn't the drive, but the failed meager test on the motor was causing an issue and either killed the drive or basically made the drive unhappy. So we needed to revisit the motor. Now in this case, we did fail the meager test, and the reason for that is this motor overheated. And when it overheated from prolonged use and poor cooling, the insulation on the wires broke down, and basically the wires have very close contact or are contacting, and so we have a voltage bleed down problem. And even though the motor practically works on the bench, the motor is throwing an error to the VFD because the VFD is sensitive to that type of current bleed down. So as a result of that, we're going to change out the motor with a new one, but that's not going to be a simple process. We need to make an adapter flange for the motor. We need to figure out a way to mount an encoder on the back, and we also need to figure out a way to adapt the current pulley to the new motor because the motor we got has a different shaft size. So this project is going to be a little bit more involved as a result of all those details, but I think it'll make for an interesting video, so we're going to bring you along for the ride.
Yeah, you can go. Go up.
For those of you who are curious, here's a meager test on a good motor. Comes all the way down to the bottom. That's coil 1, coil 2, coil 3, and we go over to the bad motor, and immediately we're going to see we have a failure. Red, red, red. So that brings us to the obvious, which is if we did this test first, why did we even put any effort into this motor when it clearly failed initially? And that may seem obvious to you guys because you have hindsight, but at the time, if we were able to fix this motor and get it running, it would have saved us a tremendous amount of work due to the mounting flange, the pulley arrangement, and the encoder. We put 1 or 2 hours into cleaning it and rebuilding it, and we wall tested it by plugging up to 440, and it did run. So with that minimal time investment, we were able to be confident enough in this motor. And when we put it on the CNC, it just didn't work because the controller is unhappy with the actual resistance of the motor. So it was at that point where we decided to switch over and purchase a new motor. When it comes to the motor selection for replacing this Taiwanese junk, we went with no other than a Vanover motor. Now, as you can see, the list price on this motor is almost $3,500, but we scored this at auction brand new, most likely surplus, for about $300. Now, there's a major difference in build quality between this and the factory unit on the fryer, and there's a couple things that make this motor just better quality overall. The first thing is this Vanover motor is VFD rated. Basically, all that means is the actual motor has cast fins, which aid in cooling compared to the smooth fan motor in a similar class. And the bearings on the motor are also rated for eddy currents, which are the currents that happen if you're actually pulsing the motor. The traditional non-VFD motors can also be run with a VFD, but they have the normal bearings and the smooth housing. In addition to that, the specs of this motor are pretty similar to this one. It's a 7.5 horsepower, as is this, dual voltage, as is this, and the RPM is 1770. This is 1725. It's pretty much the same thing. The build quality on this is made in the US, this is made in Taiwan, but as you can see, the actual mounting system is where the difference is. So somehow we're going to need to reconcile this mount with this mount, so that way we can go ahead and mount this to the machine. And this is a 1.5 inch shaft, or 38 millimeter. This shaft is 1 3/8, so we're going to need to reconcile that. And then on the back, this motor has a separate fan housing and then a little stub for the encoder. This one does not have a spot for the encoder, so we need to figure out that. The first thing I'm going to do is try to figure out what we're going to do about this face flange and design something up so we can start on that. I'm going to remove this front housing. Maybe we can reuse it. If not, maybe we'll just use it to measure off of. We jumped into Inventor and created a drawing for our new flange. Unfortunately, this flange isn't as straightforward as I would have liked. If we were to use the bolt hole pattern on the fryer motor, those bolts would actually contact this Vanover motor because the diameter of the motor is larger. In order to accommodate that, we actually ended up increasing the diameter of the flange by about an inch, 1.25 inches, and we pushed the slots as far to the edge as we can. That should allow us plenty of clearance to get those bolts in, but as a result, we are going to need to drill and tap 4 new holes on the head of the fryer. I went back and forth several times, and unfortunately, I don't think there's a way around that. The way that Fryer sort of solved that problem is by using this custom stepped flange, but because we don't have that, this is the solution that I think will work pretty well. We went ahead and added some flats just like the Fryer had, and I added it on both sides. That way our large flange doesn't hang off the back or hit the drawbar on the front. So I think it's going to work out super well. Let's go over to the material, and we're going to be using some 11-inch aluminum to get this thing made. that we got the pancake faced on both sides, we're gonna come in here and turn down the step. We'll do the OD last by putting it on an arbor. So we're using just a little center cutting end mill to create a spot for the boring bar, and then we'll bore out to create our step. Alright, all the features on this are turned except for the OD. I run into this problem a lot on thin parts. We could machine a little bit the ways, flip it and machine the rest. Totally acceptable. We'd have a little line in there where they would touch because of the non-concentric chuck, and I really want to have this part as nice as possible. So what we're going to do is flip the jaws around. We'll turn up a small little arbor, mount this to the arbor, mount this on there, and we'll be able to turn the OD concentric to the ID, and more importantly in this case get a nice clean OD finish. All right, we got our arbor made up. It's a nice fit. Let's get our washer in here and clamp this down. We have the part chucked up over at the mill on the super spacer. We got our drawing, and we're gonna knock out our holes and slots. We're gonna start with a spot drill, spot all 4 holes. We'll drill it with a 1/2 inch hole, maybe a little bigger for clearance, chamfer, and then we'll do our slots. Well guys, I think we unintentionally flexed when we made this. Turned out really, really nice. And this is the first time that it's gonna be unscratched, and we're gonna go ahead and install it, and it won't matter. Literally doesn't matter at all. The nice thing is when you make a quality product like a motor like this, and when we interface with it, it just makes you wanna have a sense of pride in your work and do a great job. This motor mount could have easily been cast, probably could have been 3D printed. A lot of things would have worked. So you're not gonna see it, it's not gonna matter, but it was fun to make. So we got some hardware. I think this hardware is actually a little bit short. I don't know if I ordered it wrong or whatever, but let's go ahead and see if we made a piece of junk or if it works. Should be a nice fit. Ooh, that's nice. A little tappy tap. Oh, look at that fit, look at that. It's not even seated yet. There it is, all right, cool. See if our bolt holes line up. Ooh, they look like they do. Oop. Either I made a mistake or we put this in the wrong position. I think I can work with it, maybe. The problem is this housing is so big. I tried to make this motor mount as large as possible so we could have clearance. I think we're gonna end up modifying this housing, which is fine. This is gonna work, but we're gonna have to modify the housing. So in a way, I guess we made a paperweight, but we're gonna use it. We just have a limited amount of room up there. I can't really make the slots go out any farther, and I have to make them in this direction so that way we have adjustment. So I think given the parameters, I think we're probably gonna be fine. We're just gonna have to adjust the housing a little bit, but that's no problem. We got a lathe. I should have given a little bit more clearance. These are 1/2-inch bolts and I did a 1/2-inch hole. I mean, man, this looks nice though, guys. This looks real nice. Yep, I would call that a perfect fit on the bolts. Everything is probably a little on the tight side, but it's what they call a machinist's fit. Looks excellent. We can actually get the bolts in. The problem is I want as much adjustment as possible. So I think, I don't have the bolts on me, but you can kind of see here. We could definitely get a bolt in, but we're not able to get it down because the head of the bolt is gonna contact the housing, and that's a problem because we wanna be able to slide this motor around. Here's a closer look at what we're talking about on the backside, and the more I look at this, the more I realized I made a mistake. When I designed this mount initially, I had our slots coming out radially at a 45-degree angle, which would match this notch in the casting. However, the problem with that is that I can't move the motor up and down because all the slots would be in opposition. So I went with this up and down slot, which does give us the forward to back movement we need. However, the problem is this slot, it doesn't line up with this cutout. So what I needed to do is actually do a combination of the ideas where I started my slot at a 45-degree projection from this screw hole, but I still went up and down. Now, if I did that, I'm not sure if I'd have the same amount of travel that I do with this slot, but I definitely would have landed in this casting. All right, let's open this motor up. We need to start at the rear. I want to see what the situation with the fan looks like, so we can see what we need to do with our encoder. 8mm, probably 1/4 inch. I'm guessing it's going to be pretty typical fan shroud setup, but we're going to find out. We are going to need to remove this rotor to modify for our encoder anyway. And now we need to modify the front housing as well. This motor will be a Frankenstein motor when we're done. Okay, pretty much as expected. Ooh, it's splined. Interesting. Okay, cool. Looks like these bearings might be greasable. Are you guys tired of watching me take motors apart? I know I am tired of taking them apart. Seems like we're a motor shop here recently. All right, let's see if we can get this cap off. We're gonna try to minimize hammering to preserve our bearings. Boom, there it is. As I suspected. Wave washer, very nice. Let's not forget that. Let me guess, greased on the front, shielded on the back, yep. We got these 4 screws. That's probably holding on a bearing back plate. Guess we're gonna find out if that's true. All right, now the shaft is still gonna stay on the bearing, so the best thing is to take a mallet and see if we can work this cover off. And it's probably got a little bit of paint holding it. There it is, just like we said, a little bit of a paint line. I bet I can just, man, that OD fit on that bearing is like 1 2/10. Yep, just like we said. Got our bearing, we have our grease, and we have our backing plate. Pretty typical. Looks like we have some extra meat in the casting to machine, possibly. It's like I love taking apart perfectly fine stuff and ruining it. Very carefully. Here's a shot of what the bracket's gonna look like on top of the mill. Now I need to go ahead and drill and tap 4 holes here for the slots. You can see we don't have a lot of clearance over here where the drawbar is, and on the back we're pretty much, you know, as dead as we're gonna be to the back here. So that's a very, very close fit. Actually, when we adjust this backwards, it's gonna hang off the back just a little bit, which isn't a problem, but we wanted to make sure that this got centered up and that it fits up here, and I think this is gonna work out quite well. Well, we fixed our mistake. I was debating cutting the casting on this, and I just realized if I went back and added another slot, it would avoid me having to modify the motor, and it would solve all of our problems. I would just have to retap the 4 holes I did up there, but I think this is gonna be the best solution. And hey, it's not gonna hurt that we have a set of extra slots on this. It's a learning experience. So this is what it will look like. I'm gonna get a socket cap bolt, and as you can see, we're taking advantage of the cutout, and we'll have full range of adjustment, as it kind of should be or was in my mind before I made that mistake. The nice thing about doing this is if this motor fails, we unbolt it, and we'll be able to bolt any motor to this flange as long as it's the same face and no modifications need to be done, which is good for serviceability. This was the right way to go. So this turned out good. I'll retap those holes on the fryer head, and then we'll go ahead and move on to the next step, which is going to be figuring out the encoder mounting scenario. We're ready for the next step in the motor modifications, and that is modifying the stator. These next couple modifications are going to be focused on allowing the encoder to mount to the motor via the rotor shaft. Now, currently we have an impeller mounted to the back, but what we're going to do is get rid of that impeller and run a powered fan like we previously had on the machine and utilize this shaft as an output for the encoder. So what we did is we set it up in the machine. I made sure that everything was running true on both sides. We had a center in it. I set up the steady rest. I took the center in, put it out, took it in, put it out, made sure that the indicator was unaffected. We have about 1/1000 total run out, maybe 9/10, and nothing has changed with the steady. So now that the steady is set and everything is dialed in, we're gonna come in here and use a larger center, widen out that center, and then we will be drilling and tapping for a stud, which is going to register on this new conical seat. So that way we can do an extension for the encoder, which will be more clear as we get there. For now, we're gonna come in, recut that center, and then we'll tap it 5/16/24. Very close on our ER40 holder. So we got some chips in our bearing, I feel like. All right, we extended our center out a little farther. Now we're gonna come in here and drill for a 5/16 24 letter I drill. Now we're gonna drill and tap. I was gonna do this by hand, but this tap doesn't have a center in the end, so I wanna get it started straight. I want this going in relatively straight, especially on these small taps. I want to be gentle tapping with the chuck. The reason we're doing it this way is we can use the threads to screw in a stub shaft. We'll probably use some Loctite, and that shaft will register on this conical seat. And if we ever have to service this motor for any reason, we can pull the stub shaft out and register on this center that's existing. The next step is to figure out the mounting for the encoder, and we're gonna be utilizing the housing, but we wanna make sure that the encoder is concentric with the shaft. Now this is a casting, but this casting has been machined, namely around the diameter and on the bearing journal. So we are actually going to reference off of the bearing journal. So I've chucked up an arbor and I've turned it down to 62 millimeter exactly, which is the OD of the bearing. There should be a little bit of clearance in here, about 1, 2, 3/10. So let's see if we can get this on here and what the fit is gonna be like. Actually, we're not bottoming, and I want to bottom. So I'm gonna come in here and cut a little more relief out, but that fit. All right, let's try that again. There's a register down here at the bottom, and I want to reference off this diameter plus the register. It was hitting on these nubs before, so I just cut it back a little farther. All right, looks like we're on that register. So now this should be spinning 100% concentric to that journal. So we already tapped this ahead of time. That way, any additional force from drilling didn't move the arbor around. Now we do not need to machine the dead center of this. So we're gonna just clamp in the center and machine around it. All right, that's running perfectly true. Originally, I was trying to clamp on this flange face here, but I was getting some run out. Now when I eyeball this flange face, it's running perfectly true. So we can come in here and clean up the area we need to. Just taking some light cuts, nothing crazy. Looks good. So now this face is machined flat and perpendicular to the bearing race. And we're gonna mount our mounting system to this face, but we want it to be perpendicular. All right, let's get this off here and move on to the next step. The last step is to drill and tap 2 quarter-20 holes, 180 degrees apart. And we're specifically missing these oil ports or grease grooves. We're using a number 7 drill, no spot drill. We're just gonna peck. It'll be fine. 80 millimeter bolt hole circle or 40 millimeters half. We're gonna go 5/8 inches deep, rotate 180 degrees. Gonna do a little baby chamfer. That's it. I'm gonna drill and tap here with the quill. Finish by hand. There she is. This completes the modification of the rear cover. We're gonna start on this encoder mount with just a piece of hot roll. We're gonna get it faced off, punch a hole in it. Doesn't need to be fancy. The most important part is that both of these sides are parallel. So we'll get this knocked out. Had a 433 on there, not a 432. So it wasn't chipping, needed a heavier cut. We're over here at the mill for the last stop. We're gonna spot drill. We still have this set up with our 80mm BCD for modifying the cover. So we'll come in here and do a spot drill with the wrong type of spot, 1/4-inch drill bit, and then a counter bore for our screws. And then we can drill the bolt hole pattern for the encoder. All right, M3 tab. See if we can break it.
On your lathe, yeah. You can probably get... So we're making a sleeve right now for our new motor, because the new motor is Imperial. And the original motor that came with the machine is metric, so the size of the shaft is different. So we were going to use the same original pulley that came with the machine. We're going to make a sleeve to adapt the shaft of the new motor with the original pulley.
Cool. So while Stefano is making this on the blue lathe, I'm going to be over on the pacemaker making our standoff for the encoder. So hopefully we can both knock out the part at the same time.
Kyle, what do you think?
That's pretty good.
About 6,000 per revolution. We're running at about 600 RPM.
The lathe does a good job.
People are watching, so I always wonder, you know. Very minimal back drag, so the machine is doing great.
Yeah.
Symmetric too. So we just finished machining the sleeve. Turned out very nice. That was like my second job on Kyle's lathe, but it works amazing. And we got the sleeve ready. The only thing we have left to do now is to cut the slot for the keyway, which you're going to be doing tomorrow, right, Kyle?
Yep.
And then I think we just need to assemble, because you got your spacer done. So yeah, we're good to go.
Yep, we'll assemble it, and then from there we'll work on the fan shroud and get it back together. You can start to see our idea take shape. This spacer will screw to the end bell. Right now it's kind of floating because my screws are a little bit long, but we'll trim those. We have our encoder, which will mount to this, and then we made a custom shaft over at Stefano's shop that will come in and be secured to the encoder. Now with all of that done, our end bell is not going to fit because of all these extra things we've added to the rear, and we also are going to be adding a fan in here. So we need to extend this end bell like this, about 4 inches. So I bought some sheet metal, and then we're going to use a cheap little ring roller, bend up a ring. I'll do that off camera, and we'll extend this, get this painted, and try to make it look as much like factory as possible. And we're pretty much almost done at that point, and we can reassemble. We got all the modifications done to the motor and its components, and we're ready to reassemble. Just as a quick review, we modified the cover for clearance for the encoder and the additional fan. We also modified the back plate for the encoder mount. We machined an encoder mount. We machined an adapter sleeve. We machined a stud on the end of the motor so the encoder can register. We machined a custom step key. We actually machined a custom motor mount, and then we drilled and tapped the end of the actual rotor so we could get this shaft mounted. Now that we got all that work done, we're gonna get this thing back together and see how she runs. First is the rotor. Then we're gonna put on the front cap, and I'm gonna do this first so I have a little clearance to get my hand in here for this cap. So I can slide this out so I can come back here and get these screws. All right, that's on, so we'll go ahead and slide this cap forward, and we'll get these screws started. All right, we'll turn this around. Don't want to forget our wave washer. Take our wave washer. We're actually going to put that in the housing. There we go. So we'll get all 4 of these guys in and we'll tighten it up. All right, now we install the encoder mount. Just give it a little bit of thread lock. Make sure my surface is clean. Next, we're going to install the stud. A little bit of thread lock. All right, let's get this encoder installed. It's a nice fit there. All right, let's get this cover on. Now I am currently waiting on the fan. We didn't install the fan, but once the fan gets here, we'll pull the shroud off, mount it to the back cover, and there should be plenty of clearance and the wire will come out here. We're just trying to get this thing up and running for now. All right, let's get our flange on. All right, here's our sleeve. Clearance there, which is nice. And our stepped key. And our pulley. We managed to wrestle this motor into place. It was a little dicey with one person. We only broke one Bridgeport Z handle, and I realized that this requires 7/16 hex, which I don't have, so we have to make a custom wrench. So I ordered up a 7/16 Allen key. I'll put it in the comments how much I paid for this. It's a stupid handle, but I bet they'll charge a ridiculous amount. Other than that, we got the motor in. And yeah, we hit this with the forklift when I was backing up. My fault, 100%, but stuff happens. Let's get this motor bolted down and then we'll work on the wiring. We did it. We got the motor installed and everything works perfectly. 2,000 RPMs, nice and quiet. This motor runs way better than the previous Taiwanese motor. It's quiet, it's efficient, and it's American made. And I couldn't be happier to have a quality unit on our fryer milling machine. Now, like usual, I underestimated the amount of work it took to get to this point, but I think the end result is well worth it. Now, I did start a job 3.5 weeks ago that I'm gonna start finishing up, but I wanna know what you guys think about this video. Let me know down below in the comments, and until next time, we'll see you on the next one.